Hello everyone, in this video we're going to relate linear versus rotational motion. And we're going to relate all these different variables of tangential velocity, acceleration, distance to its rotational form. And we're going to see how we do that. So let's start with this very simple equation. This is where we're going to build all the other equations off of. And so this is saying the angle equals this s, which is the distance. So if we have a circle over here, and it travels by some angle, and this is the radius. This distance we call s. And since it's along a curve, we're going to call it the arc length. So that's the actual difference travel. So if you walked around a circle and you looked at like how far you traveled, that would be this arc length. And this r is just the radius. Okay? And so let's just rearrange this equation to say the s is equal to r times theta. Okay? So this is how we can relate it through this radius here. The angle traveled, we can find the radius, we can find the distance through the radius. Okay, so now let's see how can we find the velocity. So let's say we have the omega, so the angular velocity equals the change in theta over time. And so let's say we do 1 revolution. So 1 revolution, as we learned before, if you go around the circle 1 time, the amount of degrees or radians that it's in is just 2 pi. And then the time that we use to express to go around 1 revolution, if you remember from circular motion, is just the period. Okay, so that's the period. And so that's what we have this for this angular velocity. And so our tangential velocity equation that we use from circular motion is we need the distance over time. And so the distance is just the circumference, which is 2 pi r, over the time, which is 1 revolution, which is t. And so now we have this t in terms of the tangential velocity. So we can actually go ahead and rewrite this in terms of t over vt and get this. And so now that we have the period, we can actually go ahead and plug this in over to here. And so we would get the angular velocity equals 2 pi divided by this 2 pi r over vt. And so since we're dividing a fraction, we can multiply by the reciprocal and get 2 pi times vt over 2 pi r. And so these 2 pi's are going to cancel, and we're going to get the angular velocity equals this vt over r. And so if we rewrite this, we get the tangential velocity equals the radius times the angular velocity, which is in the same form as this arc length equals the radius times the theta. And so let me just box this in as our first equation. And so now we have a way to relate the linear velocity to the angular velocity. So now, just like this is the case, we can actually find that the tangential acceleration is equal to the radius times the angular acceleration. And so that's simply the definition of tangential acceleration. Because we haven't really used tangential acceleration before, we only use a centripetal acceleration. But how are we going to relate this centripetal acceleration that we talked about in circular motion? Well, we know that centripetal acceleration equals the velocity squared over r. That was that formula that we were given. But we just made a new, and this is going to be the tangential velocity, and we just have a new equation right here that we can use. So we can plug that in where we get r omega, all of this squared over r. And so now we can square this top part and get r squared omega squared over r. So one of these r's is going to cancel. And so we will get our centripetal acceleration equals r omega squared. And so that's our other type of acceleration. So if you remember, if we were taking a circle and it's traveling with some velocity tangential, this centripetal acceleration is the one that's pointing towards the center of the circle. And our angular is how fast it's speeding up around the circle. Okay, so that's how we can relate all of them, and they're all related through this r. This is the big relator, is the radius of the circle. Okay, so we can use this to do some examples. Alright, so our first example is we have a frisbee with a radius of 0.1 meters spins at a constant 100 radians per second. What is the linear speed at 0.05 from the center? And what is the linear speed at the edge of the frisbee? Okay, so let's go ahead and define some variables first. So we know the radius is equal to 0.1 meters. We also know the angular velocity is constant, so there's no angular acceleration. And so this is our radius of the whole frisbee, but we're also asked to find this point at 0.05. So the radius, we'll say, not is 0.05 meters. Okay, so let's find the linear velocity at the first point first. So we know that the linear velocity just equals the r times omega. So at this first point, that's halfway in the middle of the circle. So let's say we were given a circle here. If this is the radius, if you were at this point right here traveling with some velocity, and you'll be at this point traveling with some velocity, and we'll denote this one as velocity 0, this one at 1. So this radius is 0.05 times omega, which is 100. And so we would get 5 meters per second. And then this velocity tangent at the very edge is going to be the entire radius of 0.1 times the 100. And so this tangential velocity is equal to 10 meters per second. And so when you're at the edge of the circle, you're moving twice as fast when the frisbee is spinning at the same velocity, which makes sense because if this one makes one rotation, it's traveling a shorter distance than moving all the way along this outside, but they're both making this revolution in the same time because they're connected by the frisbee. So this outside one has to travel at a faster linear velocity even though it's rotating at the same speed. Okay, so let's do part B. So if a bug lands on the edge of the frisbee, what is its angular, tangential, and centripetal acceleration? Okay, so let's start with what we're given. So we know the angular velocity is 100 radians per second. And so we know it's a constant velocity, so the change in this velocity is equal to 0. And so since this angular velocity or angular acceleration is just the change in angular velocity, since this equals 0, the whole thing equals 0, and so our angular acceleration equals 0. But since the bug is changing its tangential velocity, because at one point, if we go back to this circle, if you're at the top of the circle, at one point it's traveling right here, but then once it's rotating to here, now you have a tangential velocity going in this direction. So it's changing, so there must be some centripetal acceleration. And so the centripetal acceleration is equal to r omega squared. And so we have all these values, so we can go ahead and plug in the radius, which is 0.1, the omega, which is 100 squared, and that's going to give us 1,000 meters per second squared, and that's our centripetal acceleration. And then finally the tangential acceleration, which is equals the r times alpha. We go ahead and plug this in, and we get, since this alpha equals 0, this whole thing will equal 0, and the angular or the tangential acceleration will equal 0. Alright, that is all I have for this video. Thank you for watching, and I will see you in the next one.